Todos ustedes lo tienen muy claro, los avances en materiales para la construcción de puentes y los métodos constructivos han sido probablemente los pilares de un desarrollo muy notable. El día de hoy tendremos la oportunidad de escuchar al doctor Cremona, que nos hablará principalmente sobre estos temas. El doctor ha dedicado buena parte de su vida a la investigación de los materiales. Para tener una semblanza del doctor Cremona, me voy a permitir presentar a ustedes brevemente su currículum. El doctor Cremona es actualmente el director de investigación y desarrollo en la constructora Puentes y director de ingeniería de materiales de la misma empresa. Él está también a cargo del Consejo de Ingeniería de Puentes y en las obras públicas de la misma empresa. Hasta 2015, el doctor Cremona fue director del Centro Técnico para Ingeniería de Puentes en la Dirección Técnica de Infraestructura de Transporte y Materiales. En el Centro de Estudios y Experiencia en Riesgo, Ambiente, Movilidad y Planeación Urbana y Rural. Después de más de 15 años en investigación en el Laboratorio Francés para Carreteras y Puentes, él se desplazó a la Dirección de Investigación e Innovación del Ministerio de Ecología, Sustentabilidad, Transporte y Vivienda, donde administró las actividades francesas y europeas de investigación en el sector de la ingeniería y la construcción. Sus campos de interés son el desarrollo de métodos avanzados para la inspección, conservación y observación de estructuras ingenieriles. Es constructor y experto en proyectos de puentes y participante en grupos nacionales e internacionales. El doctor Cremona también está a cargo de actividades académicas en cursos de maestría y doctorado. En 2004 recibió el Premio Internacional de la Asociación Internacional de Puentes y en 2003 el Premio Francés de la Asociación Francesa de Ingeniería Civil. Él escribió o editó por lo menos 5 libros y más de 200 artículos y el gran número de conferencias y en revistas. Los dejo a ustedes con el doctor Cremona.
Thank you, Mr. Chairman. Well, ladies and gentlemen, well, I'm very pleased, to be here. And I should like, to thank, the AMIFTAC Association and Dr. Patron Solares for their kind invitation, for making, this keynote this afternoon on new materials for bridge engineering. Well, firstly, what I'm going to say, can be easily expanded, to other types of constructions, and not only bridges, even if my presentation will be focused on essentially on bridges. And secondly, novelty can be related really to something new, to a real progress in material engineering, or can be related also to an existing material but that is not widely used. And during my presentation, you will find both type of materials, well, something relatively new, or some others that are not new in the sense that they have been developed, well, 20 years ago, but anyway, they are not widely spread, well, in the construction. Well, for a long time, well, innovations in material engineering were driven by mechanical properties. It is what I used to say, well, the quest for strength and also for weight, but both are generally very related. Today, or let us say, well, for the past 20 years, it is also driven by other concerns: durability, it means longevity, and sustainability, where the economical, the environmental, and the social aspects are also very important. So the quest today for material engineering is not only strength, but it also durability and sustainability. There are also, well, different set of requirements for innovation in material engineering. That you have requirements for an efficient and effective repair materials, and this is a strong concern in developed countries where you have, in fact, infrastructure decay problems. But you have also requirements on material durability, sustainability, as well as construction efficiency, now for new materials or for new construction in developing countries. I'm not going to talk too much about, well, repair materials because, well, it is a keynote by itself. So, in fact, my presentation is mainly focused on materials for construction and not for repair. Let us go back, well, to some basics related to material engineering. You must know that there are three classes of materials, and any materials, in fact, you are elaborated, are in fact belongs, well, to these three classes of materials. You have metals, you have polymers, and you have a big family where you can find, well, composites and ceramics. But when you choose a material, you have, in fact, to compare different aspects. Of course, the performance, and I shall come back later on these different aspects, the performance, the physical and the chemical properties, the composition, the structure, the way to process it, and, well, its synthesis. My presentation is not, in fact, well, to make, well, a list of the different materials related to these three big classes of materials, but I tried, in fact, well, to handle this presentation through different visions that could explain easily why there is some progress in material engineering for construction and for bridge engineering. And this is why, in fact, well, my presentation will be divided in four big parts. One is, in fact, well, a vision driven by strengths. The second one, it is what I call the durability vision. The third one is the saving resources vision. And the last one, and maybe, well, something that is more related to future, the smartness vision. So you will see how the different materials used in bridge engineering, in construction, in a wide sense, belong to these four visions for materials progress. As I said, well, when you want to choose a material, well, you have, in fact, well, to compare different aspects, and the first one is the performance. Performance is not a sort of intrinsic property. It has to be discussed in the context of an application. What is the function of the element? And of course, well, the material performance will be related to the function you want to achieve. And of course, well, you have, well, some questions that can be raised. What are the limitations in terms of size, weight, temperature, loads? What are the essential conditions that you cannot negotiate? But you have also some negotiable conditions. What are the objectives you want, in fact, for the element? Is it lightness? Is it the cost? Is it safety? What can be optimized? And what are the degrees of freedom? About the size, about the material type, about the manufacturing process. So these, in fact, are the basic aspects, the basic elements you have to take into account if you want, in fact, to assess the performance of the material within a specific design. The second set of aspects are the physical and the chemical properties. Physical and chemical properties usually provide quantitative data that can be used for performance assessment. So anyway, this property can be constant, can be vary or in the direction of materials, so you know all that. You can have a linear behavior or not. But anyway, you have a wide range of physical properties: acoustical, electrical, optical, radiological, magnetic, mechanical, thermal, and manufacturing properties. And also, this is quite new, a long-term vision about the longevity of these properties. Of course, well, in structural engineering, we are not interested by all these properties, and sometimes, well, one or two are useful for the designs. Regarding the chemical properties, in fact, what is important is really to describe what chemical reactions are likely to occur. And of course, well, how you can get your material, what will be the transformation in order to obtain your material. And of course, well, in most of the time, in fact, you have, well, a non-reverse process. I just want to show you these charts that are quite interesting. Well, maybe they are quite difficult to read, but in fact, well, these charts are being drawn by Professor Ashby from University of Cambridge in the 80s. He wrote a famous book about, engineering, materials engineering, and it relates, well, different properties, especially mechanical, but also electrical properties between themselves. And they show, in fact, well, how is the evolution of the different materials. What is interesting also, well, in this figure is you see, in fact, you have, let's try this one. Okay. You see here, you have, in fact, what is called performance curve. And these performance curves, in fact, well, are a sort of indicators about, well, the efficiency in the material. And of course, in fact, well, when you have a relation between density and strength, what you are looking is, in fact, well, is the highest strength and the lowest density. And usually, well, in fact, you see that all the materials that are used today are, in fact, well, on the upper part of this curve. Well, let's go further. I talk, well, in the introduction about the composition and the structure. The composition, in fact, reveals, well, the chemical elements that are present, well, in the material. And of course, the simplest pieces are the atoms. Compounds, well, is in fact, well, it's a uniform composition of different materials. So no matter how small is, in fact, the sample, you have the same elements in the same proportions. It's quite different of mixtures, and we are using a lot of mixtures well in construction, especially concrete, because in fact you can have different proportions, and because you have different proportions, you are going to have different properties. I talk also about processing and synthesis. Processing could be very simple, as hammering a piece of copper, or it can be very sophisticated. For instance, well, if you want to melt sand, well, and to form glass, you have a complete change, well, in the arrangement of the silicon and oxygen atoms. Synthesis is really a major change in the chemical composition, and the polymers are a good example. And of course, today I have to add something else, is in fact, well, sustainability. I mean, is to assess what could be the environmental impacts of your materials when you do a processing, when you do a synthesis, or when you use it. And of course, well, what could be the economical and the societal aspects when forming these different materials. So this large, well, introduction is just, in fact, well, to remind that, in fact, when you have to compare materials, you have in a design or in a construction, for using in a construction project, you have, in fact, well, to take into consideration all these different aspects, performance, of course, well, the physical and the chemical aspects, but also processing and synthesis. As I said, well, I have, in fact, well, structured my presentation into different visions or different searches or quests, and the first one is a search for strengths. You have here, well, the famous, well, Ashby chart, and you see how here, for instance, you have a big hole, because if you compare density and Young modulus, you want, in fact, well, this is a place for material development, because you want, for instance, decrease density and, well, increase for Young modulus. So you see that there is still a lot of progress, and most of the materials are, in fact, well, quite aligned, well, and there is still, in fact, work to do and step, well, to go further. In bridge engineering, well, the search of strengths, well, has been, in fact, well, related essentially, well, to the development of high-strength concrete and high-strength steel, and more recently about the use of carbon fiber reinforced polymer. And this is what I'm going to present you in this part related to the vision for strengths. High-strength concrete. In fact, well, you have high-strength concrete in one side and high-performance concrete in the other side. Today, in fact, well, both concepts are used, well, simultaneously. In fact, they are not synonymous, because high strength, it's clearly a vision how to improve the strength of the concrete. High-performance concrete, it's a bit more controversial because it means high workability, high durability, high ultimate strength. So it's not necessarily related to strength. What you are looking for high-performance concrete, it's something else than just, well, high strength. But today, well, I have to say that because of the progress, well, in material engineering, both definitions are used, well, simultaneously. Well, high strengths, well, in concrete are made possible because, in fact, you reduce porosity, inhomogeneity, and microcracks. This is why you can tackle high strengths. And of course, when you have a densification of the interfacial transition zone, well, between aggregates and, in fact, well, the cement, In fact, you have, a better, more efficient load transfer between the cement mortar and the aggregate. And this contributes, finally, to the strength of the concrete. But in that case, for a very high-strength concrete, where the matrix is extremely dense, the aggregate is at the head, finally, the weakest link. This is not cement paste, but it is, in fact, the aggregate. That is the weakest link, well, the weakest element in this system. Well, the use of high-performance concrete in France, well, is now, 30 years old because, well, it's coming from a national research project called New Ways for Concrete. And the first use or the first application of high-performance, high-strength concrete was made in 1986, and during the following 10 years, it has been used, well, only for large bridges. You have here, well, some examples, well, on these slides. There are several reasons for that, because, in fact, well, the construction method was facilitated, and, of course, well, you have also an early age strength. And the high-strength ductile material was formulated by combining Portland cement and slag or fly ash. I shall come back later on that point, but, well, this is why, in fact, there is a confusion between high-strength and high-performance concrete, is, in fact, you improve a lot also the durability of this material. So you see here in this table a comparison, for instance, well, between a reference bridge and, well, a bridge with high-strength, high-performance concrete. While you see that, well, this is a last line, well, or the two last lines, well, a reduction in pre-stressing and a reduction also in deck weight for the same design. You have here, well, a view of different bridges that has used, well, high-performance concrete. Well, the Normandy Bridge, well, the Millau Bridge, well, for, well, oldest or more recent ones. Well, you have here, well, finally, well, it has been widely used for large structures, and, well, this development in France was quite rapid. It is also used, well, on composite bridges for decks. So, well, the use of high-performance concrete, well, has been also privileged, well, for composite bridges. I'm moving, well, to another type of concrete called ultra-high-performance concrete. Well, it was known at the beginning as a reactive powder concrete, and it was a high-strength, ductile material formulated by combining has a high-performance concrete, Portland cement, silica fume, but also fine silica sand, a high range of water reducer, water, and also, for the recent development, steel or polymer fibers. Well, the properties are, in fact, well, very impressive when you compare them, well, to concrete, because you have compressive strength that can be up to 200 megapascals compared to 25, 35 megapascal. You have, in fact, ductile material. You have high bending tensile stress, reduced creep, and an increased resistance to abrasion, erosion, and corrosion, and an improved steel concrete bond compared to the usual or the reference concrete. The first studies were made, well, at Bouygues, well, in the 90s, and, well, the first bridge built with this type of material was in 1997 in Sherbrooke. Well, it was a footbridge. You have a view on the bottom part, well, of the slide. It was between 97 and 2000, well, optimized, well, through a partnership between Bouygues, Rhodia, and Lafarge, and now it's known, well, for under the name Ductal, developed and sold by Lafarge. And in 2000, 2001, there was, in fact, well, an application on a project. It was the Bourg-les-Valences Bridge. So the characteristics, well, as I said, is in fact, well, a high compressive strength. And you can have, well, steel or polymer fibers, and the fibers can be, well, can have different size and can provide usually high strength and usually used with a high concentration, especially for ultra-high performance concrete. You can have, well, fiber reinforced concrete, but in that case, well, in fact, well, the concentrations are lower and the length, well, of the fibers could be longer. But here I'm talking essentially about ultra-high performance concrete with steel or polymer fibers. You have here some examples. In fact, well, it's you have, well, here, in fact, one of the first, well, designed by Bouygues outside France, well, is, in fact, the Seoul footbridge. But finally, well, except Bourg-les-Valences and the High 51 footbridge and the Montpellier Bridge, you have a few structures, one in EHPC in France. It is now more popular than before because, in fact, well, some architect try to use it in some designs, well, for buildings, but also for bridges. And, well, it is starting, well, to be a bit more popular than it was before. There are several reasons for that, because, in fact, well, it's, of course, well, there is a question of cost, but there is also a question of workability regarding, in fact, well, the use of this material. And if you compare, well, a classical for Bourg-les-Valences, a classical design. Thank you, Albert. A classical design, with high-performance concrete and with ultra-high performance concrete, well, you see, in fact, well, the gain, well, in deck weight and also, well, in the pre-stressing, but also, well, in the reinforcement. So, well, this is, in fact, well, a very interesting, well, a comparison, because it shows that, in fact, well, you can have, well, and I shall come back later on that point, some resource savings when using ultra-high performance concrete. I'm moving now, well, to high-strength steel. There is also, well, a huge demand for higher strength steels, and steels with very high strength up to 1,000 megapascals, are available. And, well, they are, of course, produced by a specific, well, quenching and tempering process. Higher amounts of alloying elements, well, results to higher hardenability. But there is a higher risk of brittle fracture, and when you use, well, these types of high-strength steel, well, in welding structure, you can have, well, some hydrogen-induced cracking, especially if you are, well, you do not optimize your welding parameters. This explains why usually, well, this type of steel, well, with 1,000 megapascals as strengths are not used, and usually lower grades, well, up to 700 megapascal yield strengths are generally used. It is much more moderate strengths, but you have an excellent weldability. You have also, well, a specific, well, thermomechanically controlled process in order to produce this type of strength grade. And well, you have quite very interesting properties, and you can avoid, well, the problems I mentioned before regarding very high strength steel. Usually in France, well, 355 grades are used, but you have a regular implementation of high steel strength steels. 420 or 460 grades. Well, in some design, you have here, well, the Millau Bridge, Normandy Bridge, well, Gustave Flaubert Bridge, that have been used, well, 460 grades. What is also interesting today is the implementations of what we called, well, high-strength steel hybrid beams. What are hybrid beams? In fact, you have, well, in the beam, the upper flange and the lower flange that have a specific grade, and the web can have another grade. So, for instance, here you have, well, a design we made, well, some years ago in Cetra, well, where you compare, you have, in fact, well, an upper flange in S460, and the bottom flange also in S460, but the web is in S355, so in, well, traditional steel. What is interesting here, in fact, we made a design by using high-strength steel and also ultra-high performance concrete for the slab. And you see, well, in this table, well, the reduction, well, in the concrete slab in terms of weight, in terms of structural steel, and in terms of, and, well, the total, the bridge weight, you see, you have a gain of 25%. It is like, you have, well, in cars, concept cars, well, in that case, where you have more what we call, well, a concept bridge, in fact, where we test, in fact, different, well, innovative solutions regarding, well, for future design. Now I should like, well, to talk about fiber-reinforced polymer. This is less common because, well, fiber-reinforced polymer composites are quite new material in bridge engineering. This also implies, well, new detailed design methods and completely new fragmented supply chain in civil engineering. You have a lot of benefits. You have a freedom of geometry. You have also a lightweight structure, especially when you have to replace deck. You can maximize prefabrication, and you have high strength. And I shall come back later, you have also low maintenance because you have a very high durability. You have different ways to approach the problem of RP. You can, for instance, well, replace the reinforcement. The problem if you replace, well, reinforcement, and this is usually to avoid, in fact, corrosion, potential corrosion. The problem is, in fact, well, you can have FRP bars that have, in fact, low ductility. You see, in fact, well, you have a lower strength, well, for steel, but you have, in fact, a high ductility. But if you take reinforcement, well, with FRP, well, you have, well, a higher strength, a different wearing modulus, but you see you have a sort of brittle behavior, and consequently, well, you have no ductility. And of course, you have an anisotropy because, in fact, the fibers are oriented along, in fact, well, the direction of the bar. So this is, in fact, a problem if you want, in fact, well, to build reinforced concrete bridges with FRP reinforcement, because, in fact, well, you have different properties compared, well, to the steel. So you have, in fact, your way your design methods. You can also build full FRP bridge. This gives you some examples. I'm sorry, I have no example in France. I just heard that, in fact, there is one bridge in France that has been, well, recently built. It, in fact, well, it came from the Netherlands by truck, and then it was installed in a private estate. But in fact, if you go to United States, or if you go to UK, or in Germany, or in the Netherlands, you can find, well, this type of structure where, in fact, well, you have composite fiber reinforced polymer used, well, for decks. And in that case, in fact, well, it was a replacement. You see, in fact, the composite deck, and in fact, it is also covered by a structural glass. You can also use, well, CFRP for cables. You have an example in France. This is the Larouin footbridge. It was Fressinet who, in fact, will design, in fact, well, the cables. And, well, the carbon fiber cables, well, provide high strength, well, stiffness and low weight in combination with high fatigue resistance and durability. And durability is one of the major advantages for this type of material. And, of course, the low weight helps, well, to minimize, well, the sag of the cable. So if we go further in this search of strengths, we can enter now in a new field where, in fact, well, we introduce, well, nanomaterials. There is a lot of expectations in the use of nanomaterials in material engineering, and especially in construction. For instance, well, by replacing steel cables by much stronger carbon nanotube in suspension bridges or cable-stayed bridges, but also the use of nano-silica or nanotubes to produce dense cement composite materials, or use nanoclays in concrete to enhance, well, plasticity and flowability. So in concrete, well, carbon nanotubes can increase the compressive strength of cement mortar, and in steel, the addition of copper nanoparticles can, in fact, well, limit, well, the number of stress risers and fatigue cracking. I shall come back on these problems of nanomaterials because you will see that, well, it changed drastically the way to conceive structures. As I told you, well, after the search for strengths, there is another search for durability. And I'm going to present some of the same materials, but not on the aspect related to the strengths, but also to the aspect of the durability. So for instance, well, if you compare, well, traditional concrete with high-strength concrete, well, high-performance concrete, and ultra-high-performance concrete, you see that, in fact, well, if you have a look on the diffusion coefficient, that is, in fact, a driven parameter for chloride ingress, you see that you move from, well, 10 minus 11 to 10 minus 14. So in fact, well, you have a high durable material, especially in relatively well to the penetration of aggressive agents. It's the same for carbonation, because if you have a look about, well, carbonation test, accelerated test after 1 month, you see, in fact, well, the ingress is very small. So I'm not going to talk too much about, well, high-performance concrete, because I said a lot already on the strength side, but you see that on the durability side, there is an important, well, step forward in the use of this material. There is also, in terms of durability, there is another search or quest is the resistance to corrosion. So to use more resistant steels to corrosion, for instance, the use of self-weathering steel or stainless steel, or eventually, as I said, to replace fully steel by fiber reinforced polymers. For self-weathering steel, in fact, well, the objective is, in fact, well, to have a steel that has a protective layer on its surface, and of course, well, it's a sort of corrosion retarding effect produced by a particular distribution and concentration of allowing elements. So this is a layer that is developing and regenerating continuously when subjected to the influence of the weather. So it is a sort of protective coating. You have different examples in France. The first ones were built well in the 80s, and it's now starting to be a bit more popular after a period where it was not, it does not interest architects or engineers, etc., or designers. Well, now it's becoming more and more popular, and you see that some projects in 2010. Or you have here, the view, in fact, of a bridge that has been built over the A86 motorway in Paris very recently, and that is carrying a tramway. So you have 40 bridges built since 1968. You have a general good behavior. So in fact, the coating layer is functioning very well. You have, some localized degradations. Usually it is because, in fact, you have some water stagnation. It is 10–15% more costly, but you can save important maintenance savings. And at the end of my presentation, I shall explain that, in fact, you need to have a global view of this problem. Duplex stainless bridges, you have, in that case, also a better strength, but also a better durability, and you have similar qualities in terms of weldability and fatigue resistance. It's not very common in France. You have here, an example in Saint-Brieuc and so on in the north of France, and another one is a footbridge in La Défense. The cost is one of the major problem. And, but anyway, it is sometimes, the choice of the architects, to have, this type of material quality in terms of structural appearance. For fiber-reinforced polymer, you have the durability, you have a high durability, and finally, because in fact, it's corrosion-free in some way. And of course, this can have a strong consequence, in terms of maintenance. Regarding nanomaterials, for concrete, in fact, the addition of nanosilica, and it is already done, to cement-based materials can lead to improvement in durability. For steel, if you use some specific nanoparticles, you can, in fact, improve the delayed fracture problems and reduce the effects of hydrogen embrittlement, and you can improve, the steel microstructure. You can use also nanotubes in concrete. The objective of the use of nanotubes is to prevent cracks. The problem with nanotubes, usually it's not provided at the nanoscale. It is usually provided in a small aggregates and less than 1 centimeter. And in fact, you have to delay these small aggregates in order to produce a mixture that is homogeneous with your concrete. So if you perform very well, you got this type of profile where you have the nanotubes that are connecting, in fact, the different pieces, in fact, of your, of the composition of your cement paste. But if you do not delay properly, you have, in fact, some aggregates of nanotubes, and in fact, you lose any efficiency. There is also a search for saving resources. So, in fact, what we want today is, in fact, this is related to sustainability. We want to reduce the carbon footprint of concrete. This has already been done, finally, in high-performance concrete and ultra-high-performance concrete by replacing clinker by slag, ash film, etc. But, in fact, you can also replace clinker by metakaolin. And you have, in fact, an example of a bridge where, in fact, some metakaolin has been used in the cement. And this is, in fact, the Chambon-Delmas bridge in Bordeaux. And with the use of metakaolin, you have an increased compressive and flexural strength. You reduce the permeability. You have, well, a reduced potential, well, for efflorescence, and you reduce the effects of eventually, well, alkali silicate reactivity. And you have, well, some interesting properties, well, in terms of workability and finishing of concrete. I have to say that, well, we are, well, in Bouygues, well, trying to develop the use of this material, especially, well, in different projects. Because, in fact, well, the new standards for concrete, well, allowed, well, to do that with a certain amount of substitution. Not going to discuss this one. I'm going to talk about timber bridges. You can be surprised that I'm going to talk about timber bridges because timber is not a new material by itself. But as I said, well, in fact, well, it is something existing, but, well, the use is quite new. And in fact, well, there are some advantages, well, to use as a bridge material. But I have to say that, in fact, why we are interested in timber bridges is because, in fact, you have a lot of requests by bridge owners to have sort of more environmentally friendly structures, and timber, well, could be interesting, could be on certain aspects, because, well, you know that it is a CO2 trap, because, well, it has a good score when you do a life cycle assessment of this type of structure. But of course, you have some disadvantage. You can have a decay properties that are decaying, insect attacks, or combustibility. But you see here, well, sort of design. In fact, we try to make well, standard bridge with standard timber bridges. So because currently it is, well, quite costly to make timber bridge, so it is interesting, in fact, well, to optimize the standard. I wanted also to talk about, well, the multifunctionality. Well, the multifunctionality, it is something that is, well, already known, well, for some components. I gave, well, very basic two basic examples because they are very clear. For instance, well, you can combine, well, for this type of cable and encourage, well, strength, dehumidification, fire protection, etc. This is, in fact, the combination of two functions, because the multifunctionality is, in fact, to combine different functions. Here, for instance, well, you have, well, a shield where, in fact, you combine, in fact, two, you have, well, on this type of cables, well, the cable and a fire protection. In fact, well, this is a bit tricky because, in fact, well, in reality, you have not one component. You have, in fact, two components in that, or different components, well, to achieve the multifunctionality. But it is the same when you do monitoring, for instance. Well, in monitoring, well, you can monitor, well, when we talk about smart structures, is because, in fact, well, you have the structure and you have, well, different instrumentation components, well, to monitor the structure. But in fact, it is also very tricky because, in fact, you have two functions, but in fact, well, made by two different components. What is the real revolution? In fact, the real revolution is, in fact, well, to have really smartness materials. And what are smart materials? And in fact, materials where you have also a sensing part. So materials that can provide information on its current condition or else. You know already, well, embedded optical fibers, but you have now, well, piezoelectrical materials. You can have also smart composite materials by tagging, and you can have also electromagnetostrictive, well, materials for vibration controls. You see, well, this is a case of, in fact, well, smart material where in fact this resonant microcantilever beam is included in fact in a sort of aggregate. You can have also actuating materials, you know, for instance, the shape memory alloys. And now, that is certainly the most advanced part, the use of self-repair materials. Materials that can repair themselves, for example, through the automatic healing of cracks. You have here, in fact, two different of self-healing materials. One is, in fact, you have microcapsules in the material, and when you have a crack, in fact, the crack is opening the microcapsule, and you release, in fact, a specific colloidal component that is going, in fact, to close your crack. So you see here, in fact, the view of microcapsules, broken microcapsules. And what is today, the most advanced development is the use of bacteria. And the use of bacteria, you have here, a view of a concrete. In this concrete, the black dots, in fact, are aggregates replaced, in fact, by specific aggregates, where inside, in fact, you have, in fact, bacteria and a specific compound. So when you have a crack that is crossing this aggregate, in fact, you are releasing, in fact, the compound and the bacteria, and because, in fact, you have a water due to the permeability, in fact, you close, in fact, the crack. So these are, in fact, quite advanced, materials, and, they are now starting, in a sort of processing and, developing phase, for a more extensive use. But of course, you can combine, as I said, functions. For instance, you can incorporate, nano titania to produce a catalytic concrete. And you know, for instance, this is very common, in fact, today, to use nano titanium dioxide, especially, to improve, air quality. We have been requested last week, for a project to use nano TiO2 because, it was one of the requirements of the architects, because, it's going, to be a project, a use project. It's not in bridge engineering, it is in building, and in fact, it was a request from the architect. And you can also use, the electrical properties of carbon nanotubes that can be used for health monitoring and damage detection. So you see in this presentation that about, nanotechnologies and nanomaterials, that in fact some are already existing. It's not fully employed. You have, in fact, to develop the process and the workability of the material, but it is, it is existing and it can be used. Some other are, in fact, more, for the future, but I have to say that it is not driven by civil engineering, it's driven by other engineering fields, this type of progress. And I should like to conclude about, another search that I call the search for globality. I said to you that when you want to choose a material, you have to compare different properties, physical, chemical, performance, etc. What is usually done is usually, in fact, for instance, when you do a design, you have a different scenery. But you use, of course, different standards, codes, etc. And in fact, according to the cost of your project, you make a final choice. But in reality today, you cannot just rely on what could be the construction cost. You have also to take into account, what could be the cost and the impact, over the bridge lifetime. And this can change completely the way that you can use our materials, or you can choose materials for your design. I just give you an example. I'm just going to talk about, well, this family. We made some years ago, well, a big comparison between different between different designs for composite bridges. And we compared all to a reference bridge, and we made some different designs by using high-strength steel, using self-weathering steel. We tried to oversize the steel structure, etc., by including a third lane. And we did that for medium span bridge, small span bridge, and long span bridge. I'm just going to show you what we can get for when you analyze, in fact, well, a bridge over its lifetime, and not only at the construction stage. You see, for instance, that here, so in fact, well, the black line is in fact the reference. So when you are, well, over this black line, in fact, you increase the cost, or you increase some environmental impacts, because we did also a life cycle analysis regarding environmental impacts. And if you are below, in fact, this curve, it means that, in fact, well, you have a gain. And you see, for instance, if you use for self-weathering steel, you have, in fact, well, it is more expensive than to use to the reference scenario. But if you have a look about how it costs in terms of maintenance over the lifetime, you see that, in fact, you decrease a lot. So, in fact, what that costs you, well, at the construction phase, you can have big gains, well, during, in fact, the maintenance and the exploitation of your bridge. So this type of life cycle analysis is very interesting, well, to show that, in fact, well, materials that you can reject because it is too costly at the construction time can be very interesting, because if it is, in fact, low maintenance, well, during the lifetime of the structure. I don't want to go further on this figure, because, well, I can say a lot regarding, well, sustainability aspects, but it is important, and this will be my conclusion. This is very in part, in fact, well, not only to analyze, well, the material you can use in your structure just for its strength, its durability, its saving resources, its multifunctionality, its smartness tomorrow, but to have a global view in terms of choice, in terms of technical, because in fact you have, in fact, to fulfill some performance aspects, but in terms of cost, environmental, and this has to be made on the life cycle of the structure. Thank you very much for your attention.